Once upon a time, I was picking vegetables and flowers from the garden, and my mind went off on a tangent. Not a math kind of tangent, a straight line or plane that touches a curve or curved surface at a point, or as I would tell my class in February, a line that kisses the curve at one point. This was a different kind of tangent, a completely different line of thought. This happens frequently to me, so I will try to alert you when my thoughts go off on a tangent. Anyway, once upon a time, my mind went off on a tangent, well, really two tangents. One tangent about Xylem and Pholem, more about that later, and the other about small numbers and solutions. Not the math kind of solution, the liquid mixture kind of solution, more about that later. Anyway, off we go on two tangents. I prepared some supplies, paper towels in case I spill the solution, flour jars, my coffee, measuring cup and a scoop for my water, blue food coloring, Post-its, and a marker. I measured 9 scoops of water into each jar. And I added 1 scoop of blue food coloring to the first jar. I filled this up pretty close to full with 1 scoop of this blue food coloring, and I'm going to put it in the jar. So there's 9 scoops of water here and 1 scoop of blue food coloring. So now what I'm going to do, since I had 9 scoops of water and 1 scoop of blue in that first jar, which made 10 scoops of liquid, I could say that 1/10 of what's in there is blue coloring. So 1 part out of 10 is blue. And I stirred it up real good. And so what I'm going to do with the other jars is take 1 scoop of this 1 part in 10, and I'm going to drop it into this jar and then stir it up real good. And then I'm going to take a scoop from that jar and put it into that jar and stir it up real good. And take it from this jar and put it in that jar and all the way down. So you can see that's really diluting. The color should be getting lighter and lighter and lighter and lighter and lighter. And now, of course, you can see blue in this jar. But I'm wondering if we're going to get to a point where we don't see the blue anymore. We may or we may not. Don't know right now. But it's sure going to get lighter and lighter and lighter. You'll see less of the blue in there. So give me a minute, and that's what I'm going to do. Tangent alert. Not the math kind of tangent, a straight line or plane that touches a curve or curved surface at a point, but a completely different line of thought tangent about the word solution, which is a liquid mixture. Looking at these 6 jars, which look clear or do not appear to be blue? In other words, in which jars can you not tell there is blue coloring in the water? Which jars would you feel safe to drink from? You might say, all of them. It's just food coloring. But what if instead of blue food coloring, it was urine or arsenic? Would you drink it? Long-term effects of arsenic in drinking water include cancer, cardiovascular disease, diabetes, and neurological disorders. The Environmental Protection Agency established the drinking water standard for arsenic at 10 parts per billion. How does 10 parts per billion for arsenic compare to the concentration of blue food coloring in the jars of water? In order to explain the comparison of arsenic at 10 parts per billion to our blue food coloring example, I need you to use your imagination. Pretend it takes exactly 10 drops of liquid to fill a scoop. Remember, the first jar had 9 scoops of water, 1 scoop of blue coloring, for a total of 10 scoops of liquid. Now there's 10 drops of liquid in each scoop. So how many drops of water, drops of blue coloring, and total drops of liquid are in that first jar? Absolutely right. 90 drops of water, 10 drops of blue color for 100 total drops. So I guess you could say that the ratio of 1 scoop of blue out of 10 is the same as the ratio of 10 drops of blue out of 100. I have a question. When I took 1 scoop from the first jar and mixed it in the second jar, what was the new concentration of blue? In other words, how many drops of blue are diluted in the second jar solution? So again, we took 1/10, which was 1 scoop, of a 1 part blue in 10 solution. So 1/10 of 1/10 is, you got it, 1/100th. Which means out of the 100 drops in the second jar, exactly 1 is blue. But of course it's all mixed together. As we repeat the process, each jar to the right will have 1/10 the concentration of blue. Enough imagining. Let's figure the concentrations by following the pattern, or multiplying by 1/10, or by dividing by 10. So the first thing that we're doing are just the fractions, and you can maybe see that that's 1/10. And we decided that the next jar was 1/10 as concentrated. So 1/10 times 1/10 gave us 1/100th, 1/1000th, 1/10,000th, 100,000th, and 1/1,000,000th. Oh no, not again. Oh yes, a tangent. We just named the concentrations of blue in the jars using fractions, but there are many equivalent ways to name them, which I call mathematical synonyms. But more on that in another video. Right now, I'm going to also name the concentrations using decimal fractions and exponential notation. Notice the pattern and imagine what it would look like to continue the pattern to the right and left. For example, what might you call the concentration of blue if there was a jar 0 on the left of the first jar? Okay, back to mathematical synonyms. So 1/10, 1/100th, 1/1000th, 1/10,000th, 100,000th, and 1/1,000,000th. So 10 to the negative 1, 10 to the negative 2, 10 to the negative 3, 10 to the negative 4, 10 to the negative 5, and 10 to the negative 6. We decided the jar on the right has a concentration of 10 to the negative 6, or 1 part per million blue. How many more jars would we need in order to model 10 parts per billion, the standard for arsenic in drinking water? Explain your thinking in the comments below. Well, we're back to the flowers I picked, and the tangent that I went off on, and the investigation, that blue food coloring in the jars of water. We're also back to Xylem and Pholem, and this is what that tangent was all about. When I was in high school, I took biology, and when we were studying plants, we learned about xylem. Those are the plant veins that carry water from the roots to the leaves, and phloem are the veins that carry food from the leaves down to the roots. Anyway, here it is years later, and I'm picking flowers to put in jars, and what pops into my head? Xylem and phloem. So you know what I did. I put some blue food coloring in some jars of water, and the concentration in the first jar was 1 part blue out of 10 parts total. And by the last jar, the concentration, I think we figured, was down to 1 part in a million. I made sure that I had white flowers in each of the jars. And I'm wondering, what do you think will happen? So here's the picture of the jars just after I had arranged them. And here's a little time-lapse photography of what happened next. Okay, this is about an hour after I took that little video. And you can see some of the flowers are really getting blue. And this is that afternoon. I had picked the flowers in the morning, but I let them set until the afternoon. And 3 of the 6 jars, you could really see the blue food coloring coming up the stems. And you can almost tell what the concentration was without even looking at the jars, right? Because some of the flowers, even the purple ones, are getting blue around the edges. Here's the flowers the next day. So that's what this whole investigation was all about. Kind of interesting, right?
Do you have questions, any noticings or wonderings? Remember, everything we've created was first imagined by someone like you. So let your mind go off on a tangent.
Please like and subscribe, and check out the links below for the lesson plan to making sense of small numbers and related videos, mathematical synonyms, and Becker bottles and powers of 10.